Welcome back. We are going to study the round of errors of the composite methods today. So let me start sharing my slides. Um, I hope you can see them now. All right. So we saw an example in our last lecture where the interval width could be computed for the composite rules for the integration, numerical integration on the basis of the required accuracy. And just to remind you, the composite trapezoidal rule needed about 360 intervals, whereas that for the Simpson's rule needed only 18 intervals. So that this is about the truncation error. And in addition to the fact that less computation is needed for Simpson's techniques because you are using only 18 interval, you might suspect that there will be a smaller round of error because the number of operations that are required are smaller in number. So you may think, rightly so, that the round of error will also be smaller. However, a very important property shared by all the numerical integration methods for the composite techniques is the stability with respect to the round of error. So let's understand this. What it really says is that the round of error doesn't depend on the number of calculations that we have performed. So let's see what we get. Um, Suppose we are looking at the composite Simpson's rule, okay, with n subintervals to some function f on AB, and let's compute the maximum bound for the round of error. Let's try to do it. So we will of course have to use this function value f of xi, and there is some round of error. So suppose the function value f xi is approximated by f tilde xi, and there is this error ei. So you have that fxi is f tilde xi plus ei, where ei is the round of error. Then we compute the accumulated error in the composite Simpson's rule. We remember we are using n subintervals to our function f on AB. So we are going to, this is the composite Simpson's rule. Since we are using the Simpson's rule for the composite way, n has to be even. So n by 2 is an integer. And we have that this EH, which is the accumulated error, this is modulus, it's the mod that we are going to take. And inside the mod, you have h by 3 and E naught plus 2 times the summation of E to j. Remember E naught and En, because they come from f of x naught and f of xn, they come with coefficient 1. Then all the even nodes, the remaining even nodes will come with coefficient 2, and all the odd ones will come with coefficient 4. So the corresponding coefficients are given to the errors as well. Okay, so we have h by 3, and then we are summing E naught plus 2 times j going from 1 to n by 2 minus 1, E sub 2j plus 4 summation j going from 1 to n by 2, E sub 2j minus 1 plus the last one En. Now we have the formula that mod of AB is less than or equal to mod A plus mod B. So we apply that here and we get that this is less than or equal to h by 3 comes out. H is a positive number, and then we apply mod to each of the terms inside. All right, that's the upper bound for the accumulated error. Now, suppose these round of errors ei, because there are finitely many, suppose that there is a uniform bound on them, and let's call that bound to be epsilon. And what we can do is that in this formula, each of the mod ei can be replaced by epsilon, and we will have a less equal sign. So we have that EH is less than or equal to h by 3 epsilon, and then 2 times n by 2 minus 1 epsilon plus 4 n by 2 epsilon plus epsilon. And when you sum this up, you see that you get h by 3, and inside the bracket you get 3n epsilon. Okay, and 3n epsilon, because the 3 gets cancelled, you just get it to be h n epsilon. And what is h into n? H into n is the length of the interval you are working with. So EH is less than or equal to B minus A epsilon. we have found a bound which is independent of h. It's a bound which is independent of n. The accumulated error due to rounding off of the values of the functions is less than or equal to b minus a epsilon, where epsilon is the bound on the rounding off errors. So if you know that the function values can differ only by some margin, then you have that the total error is that margin into the length of the interval. That's all. So for instance, a very crude bound would be that epsilon will have to be less than or equal to b minus a. After all, the function values cannot really change that much. So you will have that EH is less than b minus a whole square. Very crude bound, but you have a bound which is independent of h, which is independent of n. Okay. So therefore, even if you may actually go and divide your interval into more parts to get more in accuracy, there is no increase in the round off error. The round off error remains the same, b minus a into epsilon. The epsilon will change slightly, but ultimately you will have a bound on epsilon because of whatever rounding off method you are using. So that bound is also fixed, and then you have that the accumulated error is also fixed. This means that the procedure is stable. This is the stable procedure. As h goes to 0, there is no change in the rounding off error, and therefore this procedure is stable. Recall that the rule of numerical differentiation, that was not stable. So this is an example. I am really pleased to give you an example of a stable method. You remember that for the numerical differentiation, there was an h which was coming in the numerator, and then there was an h which was coming in the denominator as well. So you had to really make a good choice. You had to be careful to choose the value of h. You could not let h go very small, because then the h in the denominator will cause the error to grow up really large. All right, so this is what we have, that the composite integration rules are stable. The error due to rounding off is not significant, and it doesn't depend on h and n. Okay, so world is not perfect, and even though we will like composite methods and so on, there are still some problems. They are really effective in most of the situations, but one problem is that they use equally spaced nodes. This is something that we have already declared, that we are for the Simpson's rule, trapezoidal rule, and in general Newton-Cotes formulae, we need to have equally spaced nodes. And this is not always a good thing, because sometimes you may have a function which has a large fluctuation on some subinterval, and it will not have a very large fluctuation on some another interval. So you may have two subintervals where on one subinterval the fluctuation is really large, the variation is really large, and on the other the variation is not that large. And such functions are indeed commonplace, especially for engineering students like you. If you're looking at mechanical engineering, then some of these functions will describe the certain features of spring and shock absorber systems. Whereas if you are looking at electrical engineering, then you are going to look at elementary circuit problems, and their solutions will give such functions. To mention a few examples, of course, in almost every part of engineering, there are such functions which come. And for instance, one such function is y of x equal to e power minus 3x sine 4x. And I'll show you the graph of this function. This is how the graph looks like. So, if we see from 2 onwards, the function is almost 0. But from 0 to 2, the function has a very large deviation. Okay. So if you wanted to compute the integral from 0 to 4 of this particular function, then the integral on 3 to 4 seems to be very close to 0, right? Even the integral on 2 to 3 is not that large. But on the initial part, 0 to 2, there is a significant variation. So what we could perhaps guess is that the negative part of this curve below the area will have some positive part here and some negative part. Negative part looks smaller, so we can guess that it would be a positive answer, but it's still not clear what the integral is on this interval. So this is an example where composite integration would be inappropriate, because composite integration will not approximate your function in a better way. A very low order method can be used from 2 to 4, but for 0 to 4, because the functional variation is large, you will need to have many points and you will need to have, so equally spaced method will not work. If you really have the h to be very small, then from 2 to 4 you are wasting your computational time and computational energy, because there you don't really need so small distances between the consecutive nodes. Whereas you can't have h to be large, because then you don't get the correct answer from 0 to 2. So this is the problem, and for which we are going to use the adaptive quadrature methods. So the point is, how do we determine what technique should be applied on various portions of the interval of integration, and how accurate can we expect the final approximation to be? This is the basic question that we want to answer, and what we would like to do is to have the approximation of the approximation error to be evenly distributed, and that is what we would try to do. So the efficient technique should predict the amount of functional variation and adopt the step size as necessary. These are called adaptive quadrature methods. We will not study these in great detail. We will see one example of this method for the Simpson's method. So we are using this composite Simpson's rule once again, but the technique can be easily modified to other composite procedures. So that's not a big question here. So let's start with an example, and we will illustrate this method by working out how we would solve one problem. So suppose you want to compute this a to b fx dx within some tolerance epsilon positive. So we are okay if the error comes out to be epsilon, and we want to approximate this interval. So what we do is that we apply the Simpson's rule with step size h equal to b minus a by 2. So you just take a, the midpoint, and b. You apply Simpson's rule to that. This will give that there is some error, of course, for some xi in AB, and your integration is approximated by this value SAB. You know very well what this value has to be: h by 3 FA plus 4 F A plus H plus FB. H is the B minus A by 2, as you know quite well. So I am putting it as SAB because we are going to use this notation S something comma something, which will give you that particular Simpson's rule for the interval AB. Okay, so or something. And the error here, remember, is h power 5 upon 90, fourth derivative of some xi. Okay. Next step, we apply the composite Simpson's rule with n equal to 4. And step size is b minus a by 4 now. Okay, so earlier you had h was b minus a by 2, now it's b minus a by 4. So you will have a plus h by 2, a plus h, a plus 3h by 2, and a plus 2h, which is the b. This is what we have. And so you are going to apply the composite Simpson's rule, right? So Simpson's rule will be applied to a comma a plus h and a plus h comma b, or a comma b plus a by 2 and b plus a by 2 comma b. So this is what we will have. There are two s values. Now I don't have to tell you what these s values are. You know very well that they are going to give you that approximation which is obtained by the Simpson's rule. And then also we have this minus 1 by 16 h power 5 upon 90, the fourth derivative of some different xi tilde. In the earlier formula where you were applying the Simpson's rule for the h equal to b minus a by 2, you had a xi, and here we have a xi tilde. Now we are making an assumption. We assume that the assumption could be said that the xi and xi tilde are close by. This is the assumption, but even more than that, xi and xi tilde need not be close by. What we really want is that this fourth derivative of the function at xi and at xi tilde, those are close by. That is the assumption, and this is a very crucial assumption. The accuracy of this method depends on this assumption. Okay, so if this is reasonably accurate, we assume that this is accurate. If this is accurate, then this f power 4 xi tilde here and the f power 4 xi that we obtained earlier can be equated. We will have that they are the same. And so what we get is that this SAB minus h power 5 90 fourth derivative at xi. Remember, the left hand side is the approximation to integration. The right hand side is also approximation to the integration, but instead of xi tilde, we have taken it to be xi. So we get an approximation sign between. If in the right hand side, if you had taken xi tilde, we would have got an equality. But now we have an approximation, and remember that there is this minus of 1 by 16 times the value that you have for the error on the left hand side. So we can rewrite this equation to get the value of h power 5 upon 90, the fourth derivative of xi, which is now in terms of 16 by 15 SAB minus A S of A comma A plus H minus S of A comma H comma B. A plus H comma B. Okay, so we have got some value, some approximate value for the error in terms of only the S values. And now we will put this value back in the last formula that we had obtained. This is the formula. So in this formula, we have some value for the error here in terms of the remaining S values. So we put it back and we see that this is the error formula really. The integration minus the summation of those two S values, which is now approximately 1 upon 16 h power 5 upon 90 fourth derivative at xi. Instead of xi tilde, we are taking xi, and now this left hand side has the value h power 5 upon 90 fourth derivative at xi. So we put that particular value here. The 16 here in the denominator gets cancelled with the 16 in the numerator, and we get that this is equal to 1 by 15 SAB minus the summation of the two values. Okay, so this in between error has been eliminated. We have obtained that the integration is closer to the values of those two S values, the summation of those two S values, 15 times closer than the SAB is closer to the summation of those two S values. So it's like, you have SAB, its distance from these summation values is 15 times more than the distance of the actual integration from these two summation values. So the summation of these two values to f integral is much better. Let's write it once again. So what we have is that the S of A comma A plus B by 2 plus S of A plus B by 2B, this approximates the integral about 15 times better than it agrees with SAB. So if you had that this distance is less than 15 epsilon, then this distance will be less than epsilon. And then you would have found the composite value for which your answer is really indeed less than epsilon. You don't know what the composite value of integral and so on is there, but all you have to do is compute these particular values. You know how to compute SAB, you know how to compute the in-between S values and check what happens. If this is less than 15 epsilon, where epsilon was your required tolerance, then you can be sure that the integral is within the epsilon range of the summation of those two S values. This is what we get. So the summation of the S values, this should have been a plus sign here, is assumed to be a sufficiently accurate approximation. That's the approximation you were looking for. Okay. But now there could be a problem that this the difference of the S values may not be less than 15 epsilon. In that case, what we do is that we apply the rule individually. The composite Simpson's rule is applied individually to these two subintervals. That means we would divide these two subintervals further into two subintervals, use the error estimation procedure to see if the approximation to integral on each of them is within epsilon by 2, and then approximate our integral by the sum of those two things. So instead of the two summation of the two s values, you will have summation of 4 s values. And if one of them again fails to have the range that we have required, then you again divide it into two parts and once again apply the procedure to the subintervals. And now here you will ask whether the the integration has the tolerance range on those subintervals to be less than epsilon by 4, and we continue this way. So this halving procedure is continued until each portion is within the required tolerance. So let me explain this once again. You want the epsilon range, epsilon tolerance on the whole interval. We have divided it into two parts, and suppose that the integration that we had obtained, the S A B minus S A plus H minus S A plus H B, if this is not less than 15 epsilon, then of course you are not expecting that the integral value will be less than epsilon by 2 in each of them, in the whole thing. Then you apply the composite Simpson's rule to each of the subintervals, and there check the values whether that gives you the tolerance to be less than epsilon by 2 on each of them. If it gives you on one of them, you are okay with that. You work with the remaining one where it may not be less than epsilon by 2. If it is not less than epsilon by 2, divide it into 2, and on those two subintervals you ask whether the approximation is close to the actual integration within epsilon by 4. If it agrees on epsilon by 4 or one of them but not on the other, work on that, divide that into 2 and ask whether you get epsilon by 8 now on each of them. And this procedure ultimately leads to a solution in most of the cases. So actually problems can be constructed where this tolerance will never be met. There are some very strange problems which will have to be artificially constructed, because in most of the natural cases this tolerance range is met after some such steps of halving the intervals. But because at each subdivision what you are doing is that you are increasing the accuracy by a factor of 16, whereas we are only asking whether the accuracy is getting by a factor of 2. That's the only thing. The range, if you remember, we had the particular error h power 5 upon 90, the fourth derivative at some xi, but when you divided it into 2 and applied the composite Simpson's rule, there was a 1 upon 16 that came. Okay, so the error is getting decreased by a factor of 16. What we are asking is whether it is relative, the tolerance is between epsilon by 2. So you are asking it at each such subsequent step, a factor of 2 is achieved. Of course, the very basic assumption here is that the errors give you that fourth derivative at some xi. We are assuming that all those are very close by. That is an assumption that we have, and that is a very central assumption to this, and only under that assumption this method works. So for instance, if I will just give an example, for instance, if you were working with this function 100 upon x square sine 10 by x, where x is between 1 and 3, then using the adaptive quadrature method with a tolerance of 10 power minus 4 to approximate this 1 to 3 fx dx will give you the answer to be minus 1.426014, a result which is accurate to within 1.1 into 10 raised to minus 5. And how many nodes did we have to take? This required that Simpson's rule with n equal to 4 has to be performed on the 23 subintervals. And those endpoints are shown here. These are the endpoints. So you see that from 1 to 3, we looked at 1, 2, 1, 2 and 3. That was the initial thing. Then on 2 to 3, we had 2.5 and 3, and 2.5 to 2.75 and 3. So between 2.75 and 3, we did not need to have any sub-interval, because there the tolerance was within the correct range, within the accepted range. But between 1 and 1.25, you needed to have several nodes. So you see that there are many vertical lines there on the x-axis, because there we needed to have several nodes. So this is what the adaptive quadrature method will do. And we will see one more method, which is the Gaussian quadrature method, which gives a very good answer when the nodes are not equally spaced. But Gaussian quadrature method is slightly different in nature. We will see that in the next lecture. So hang on. I hope to see you in our next lecture also. Thank you.